There he is. Hi, Andreas. You're still on mute, but let's wait maybe another minute. Now it works.
Hi.
Hi. Can already start to share my screen 1 second. So I can quickly repeat James' words on the Q&A, and also when you have questions during the webinar, maybe for all the attendees. So there is a Q&A function where you can post your questions, and then Andreas and me, we will see them and try to answer them. Either we will put them at the end of our webinar, or if it fits in, we will just answer them right away. And there is also a second possibility. You can raise your hand, and then James can unmute you, and you can pose your question directly in the webinar. So then let's start. We are already 1 minute over. Welcome everyone to today's workshop on flexible additive models for survival and event history analysis. I'm very delighted to give this workshop today, since it's my first one actually. Today, Andreas and me, we will talk about Andreas' little baby from his PhD work, Pump Tools package. I worked on that since my start of my PhD, which is not too long ago. It was in November last year. Before that, I worked as a financial consultant in the industry, and I have a background in mathematics. So that's from my side. I work currently at LMU Munich at the STEP Lab, and also at the Munich Center for Machine Learning. And maybe Andreas can say a few words about him.
Yeah, sure. So also welcome from my side. Very happy to give this tutorial today. I will hand over to Johannes shortly, but just a little bit about me. So I did my PhD in 2018, and as Johannes mentioned, that was also the time when I had the first iteration of Pump Tools to be able to fit those models that we will talk about. And it started out with just a basic package for some standard settings for single event right sensor data. And since then, we have extended that to mostly all the standard survival settings that exist, so to speak. And currently I'm also at LMU Munich and the Munich Center for Machine Learning, and work on survival analysis and machine learning survival analysis. And Johannes will continue with the presentation, but as he mentioned before, I will monitor the Q&A and chat. So if you have any questions, let us know, and I will then interrupt Johannes if it's appropriate to answer the questions.
Yeah, thank you, Andreas. So let's dig in. Maybe a short overview what this talk is about today, and what we will focus on, just so that you can follow all the examples which we prepared for you later more closely. So the task which we want to do, or what our Pump Tools package does, is basically transformation of many survival tests to more standard regression tests, so that we are flexible in the methods on how we estimate, for instance, hazards. And today we focus on MJCB gums, but depending on what your objective is, what your interest, where your interest lies in, if you have any constraints, like I don't know, monotonicity, for instance, you can do that differently after the data pre-processing. And then, of course, this data pre-processing might be more involved, especially when we talk about event history analysis, and especially finally in multi-state settings where we do have, for instance, also recurrent events. But then also what we will focus on today is some post-processing. I mean, estimating hazards and transition probabilities and so on is nice. Having these numbers and being able to interpret them is also nice, but some of you might also be interested to communicate those values, maybe not to a statistical audience, but also to medical doctors. And then sometimes visualizing would also be nice too. And so we will also talk about this a little bit today. So what does exactly PAM tools do? So as I said, it's a lot of pre-processing, but then why does it have this fancy name, PAM tools? Like, where does it come from? And yeah, it's basically a toolbox, help you analyze your data. And PAM refers to the model class. So we have piecewise exponential data or piecewise exponential data, which we then estimate our hazards or other variables with additive mixed models. So this is where PAM comes from. And what are we interested in? We basically interested in the time. Time itself is another covariate. If you worked with survival data, you know that usually when you have single events, you have a time component and your event indicator. And sometimes, I mean, in the normal basic frameworks, this is enough, but then sometimes you also might be interested in more complex components in your model, like time-varying effects or time-dependent covariates. And all these covariates, all these effects can easily be incorporated with PAM tools. We will show today I mean, not mathematically show, but we have some examples where we show that it's basically equivalent to a Cox model. We obtain the same explicit estimates of the baseline hazard, but we will also illustrate in which cases PAM tools might model some effects more appropriately, because we might have some more complex nonlinear structures which we can easily model with additive mixed models. We brought a lot of examples. If you are interested, we cannot show everything this package does today, of course. We cut out some nice results, some interesting modeling approaches. But if you're interested in more, in seeing more, we have our PAM tools webpage. And there basically here in this articles, you see a list of other examples which you then can also code yourself and try to take a look into it. Maybe some of these frameworks fit your use case. And then I'm not the only one who was impressed by how PAM tools facilitates analyzing survival data. The word spread already on X. So it's not just me, a junior PhD, saying that. Some others already work with it, and we got some feedback on that. So let's continue with today's agenda. Now that you have a brief overview about PAM tools, what it does, etc., we want to first clarify why PAM tools is useful. Then we will go into how PAM tools actually can help you analyze survival data. In the third section today, we talk about the nitty-gritty R code details, where we completely focus on R code and how to produce these presented results before. And then last but not least, we will give you some outlook and summary what we did today. The scenarios which we will cover are basic scenarios, non-proportional hazards, so a little bit more involved, but still we stick to the single event case. And then in the end, we will talk about competing risks and multi-states. So why is PAM-tools useful? Basically, PAM-tools, you can calculate baseline hazards as you can do with COGS. And we brought a small example of tumor data where we have a single event. So the status is 1 for death or 0 for censoring. So basically when the patient drops out the study, but we do not know if the event already happened or if no event already happened. And then on the time axis, because we have time to event data, so we are always interested in, as the time progresses, how probable or what's the risk that this event happens. So here on the time, we have days. So this would be a very simple hazard, but we already see that the structure over time might vary. So it might not be just linear, or if it's the hazard and not the log hazard, it might not just be exponential. But here we will we already see that the decay might be stronger, weaker, and then stronger again, dependent on how much time there is. Then we will progress. As I already told you, we want to compare, PAM to COGS. We want to see if the results are actually equal, and we will do that with analyzing Veterans Administration lung cancer studies. So this is a data set from the survival package in R. There we will take a look at the treatment variable, whether or not the patient had prior therapy, or the Kanofsky performance score. And the Kanofsky performance score we first take a look into as a linear effect. Here on the right-hand side, there is a first foreshadowing how the results look like. So they are basically pretty close. But then we will build up on that and try to model the Kanofsky performance score as a time varying effect. Thirdly, now, with the linear effects, the next logical step is to progress to nonlinear effects. And for the nonlinear effects, we brought an example of the fire brigade response times in London. So here we are especially interested in times of the day, because you might think that during nights and rush hours, the response time when the fire brigade arrives at the fire scene might differ. And then also it might also differ around the city, where the density of fire brigades are not homogeneous. So in the surrounding, like in the suburbs, there might be less, so the response time might be bigger, but we will analyze them. And you will see with what code you receive these results on the right-hand side. Then, as I said, we will revisit the example of the Veterans Administration lung cancer study. We take a look into the time dependence of the Kanofsky score, and we will compare literature results with super flexible spine modeling, and we will incorporate on the results and compare the results which you see on the right-hand side. Then again, with the Veterans Administration lung cancer study, what we want also to see is stratified hazards. We want to compare different groups. This can be done with COGS, but we will also show you how it is done with PAM-tools, and that actually receiving these kind of results is not so different of analyzing, like the pipeline is not so different of analyzing any of the settings we had before. Then lastly, we will enter the event history stages with multiple outcomes. First, competing risks, where we look at ICU patients with endpoints discharge or death, or 0 for censoring again. And our event of interest is death, but it has a competing risk, namely the discharge from the ICU. So they compete against each other, because either I can see in the data the death if the patient is still in the hospital, but if the patient is released, so discharged from the ICU, I cannot see the death anymore. So these two events differ, and we will analyze the data with respect to pneumonia. And here we we'll check basically we compare hazard ratios, or we comment on hazard ratios and last but not least, we have a multi-state data set, namely the abnormal prothrombin levels in liver cirrhosis. Here, basically what we looked at, what's new is that you can either have normal prothrombin levels or abnormal prothrombin levels, and you can switch between these back and forth. And then from each of these two states, you can also transition into the death state. And since the data is built up differently than what we had before, we will incorporate how these more complex scenarios can be modeled with pump tools. So how exactly can pump tools help us now analyzing the data we just showed and analyze all these examples? Let me just give you a quick overview how to get now from the survival data towards interpretable results. So what pump tools actually does is it makes it easier to process the data. So we have in the beginning, which you can see in the input on your left hand side, we have survival data, and we need something called PED, which I will explain in a second. So piecewise exponential data, on which we then can fit various and numerous methods, which now can estimate our hazards and so on. And with these estimated hazards or transition probabilities, cumulative incidence functions, we then can make a prediction and visualize our data. And what pump tools does is basically the first thing and the last thing. And for the computation, you also have convenience functions, which just makes it easier for you to apply. But let us maybe first focus on the pre-processing and why is it's such a gain to use pump tools and not always do these transformations from the survival task towards the piecewise exponential data one step at a time. And this is important because we need this piecewise exponential data to actually exploit these piecewise exponential additive mixed models. Where does this piecewise come from? This piecewise comes into play when, I just said we have survival data, so we have time, and our endpoint is an event. And this time period we decompose in different intervals. We make basically smaller intervals, smaller time intervals, and on these smaller time intervals we assume piecewise constant hazards, which we now can estimate. And this estimation we today show you with GAMS, which means that we can include smooth effects here depicted in like this mathematical formula. I promise I have not brought many formulas today, although I'm a mathematician and I like them, but here I think it helps understanding how this hazard is estimated, or how the flexibility of GAM comes into place. So here with the sum, with this f function, basically with the sum of the f functions, we can model it very flexibly. So we here model a function which depends on the covariates and our time, but this can be smooth. It does not necessarily have to be linear. And then the first part is the baseline hazard. We will later compare them to the proportional hazard model, which basically has the same structure. And then in the last part, this B is our mixed, is our random effect. For instance, if you have patients with different hospitals and you want to account for the variation between these hospitals, you would then maybe, if it makes sense in your specific setting, that random. And now I already told you that we need this. We need to decompose the our time period into smaller intervals. And I just gave you a short overview on how this is done. I will quickly go through that. You don't have to just try to get used to the idea. You don't have to think too much about it, because we already implemented this as PED helper function in pump tools, and you will see how this transformation is done in R later in pump tools. But first, let us start. On the left-hand side, you see your survival data. In your survival data, what's important is you have your subjects, which are coded as IDs here. You have your time point when something happens, the subject drops out of your study, for instance. You have your status, it's either 0 or 1 when the event happens, or centering, and then you have your covariate, in this case, exemplary, it's age. And then what you do is to decompose the time frame, the time period. Just think about it to be very, very long data set. You define your interval endpoints. In this case, the A0 up to A3 are your interval endpoints. And then the first thing what you do to transform your survival data to a piecewise exponential data is that you just include the intervals. And then first thing you notice is that now, I mean, in the first part, your subject 1 appears just once in your data set. On the right-hand side, it appears twice. But if you look at the intervals, this makes sense, right? So this ID now appears during the time 0 and 1, and nothing happens. And then during the time 1 to 1.5, also nothing happens, but then later it does not appear again, because your maximum time point here for subject for subject 1 was 1.3. And then, as I said, you have to also transfer the status. Here for 1, nothing basically happens. You can just copy it. For subject 3, you basically just copy and paste the status for each time interval. Here we know the event happens at time point 2.7. So it happens in the interval from 1.5 to 3. And this is exactly what you see. And then for further calculation, which I will omit, you also copy the differences of the time to the interval endpoints, and you will also just copy the interval endpoints, and then you have your data in your piecewise exponential data format. But as you can see, I mean, this is very it's somehow intuitive if your task is simple, but if you think about competing risks or multi-state, where your subjects are can transition forth and back, this might be tedious, and that's why basically there is already a function in pump tools. And this now we come to the first example where we dig a little bit deeper. So here with the back to the tumor example where we estimated the baseline hazard, you can see that basically here on the bottom left, we just load the data, it's tumor data with this time to event, timestamp and event stamp. So days is time and status is basically our event. And then with SPED, we can simply create this piecewise exponential data. And based on this piecewise exponential data, we can now fit a GAM. And this GAM, so for generalized additive model, we can plug in the formula. We want to predict the PED status. Here we do this depending smoothly on our time t end, which is the interval endpoints basically, which can be which are created in this SPED data set. And if you don't specify further what interval endpoints you want to take, it just takes per default the time points you have in your data when you have basically here the, like, for example, in this case, it would be 1.3, 0.5, and 2.7. And then, okay, here, I mean, this formula is quite involved. It's quite big. You have to think of your distribution. You have to think of the offset, which is basically the reason why we have this time here, why we have this time here. But this, if you know what it means, it's fine. But in the end, typing it down all the time is, after the third time, there are better things to do it, to do with your time. So there is this convenience function, which is called PUM. And here it basically works the same way as when you modeled with Cox pH. It just, it's basically this function you see here at the top, and just with a simpler code. So you don't have to think about the family, you don't have to think about the offset. And then the nice thing is, now if we want to do a prediction, so this first part, the PED part, when you remember our pipeline, this would be the left part, the pre-processing. This part in the middle with the PUM function, this would be our estimation part where we estimate the hazards. And then on the right-hand side, we want to do prediction. We want to do visualization. And this is the bottom part where we build our make new data set. So basically here we just use all the time points we have in our data. You can also use some sequence of days. You can use the age if you want. So you can use whatever you like here, and it builds up your data set. And important thing is that here your variable where you want to evaluate your hazard is included. Basically here you build up your data set with a lot of data points, and for each data point you evaluate your PUM object. And because you do that, you can then easily also add your hazard with confidence intervals. And now you have a data set which is called hazard underscore data frame df. And there it's in there is the time, the hazard, and the confidence intervals of the hazards. And this you can then plot easily with ggplot on the right hand side. So this is how we created this plot. And that's also basically all the code you need for that.
Yeah, just briefly, Johannes, as an addition. Yeah, so when I started to write the package or just working on survival analysis, it was just often annoyed how complicated it is to produce predictions, for example, for the hazard rate or for a hazard rate for a specific covariate specification or survival probabilities. So I thought about how to make this like easy but also flexible. And that's the way I came up. So you use the data set that you use to fit the model, and then using make new data, you just specify whatever covariate specification you're interested in. So in this case, we just say we want the unique event times, and then we calculate the hazard for these unique event times, but you could also specify further covariates. And then there are a couple of add functions. So add underscore, as you can see here, add hazard. But as you will see later, there are also other functions like add survival probability, add cumulative hazard, add CIF for the cumulative incidence function and computing risks, etc. So you always use the same workflow to obtain a data set, add the predictions from the model, and then you can use your favorite tool for visualization. Yeah, so here we use ggplot, but once you have the data with the predictions, you can use whatever you want. And I think it's just flexible and user-friendly on the one hand, but on the other hand, you can still use your favorite tools for visualization and be very flexible with that. Sorry.
Yeah, thanks, Andreas. No, these insights are always interesting things. Yeah, and about the flexibility, maybe this is also the correct way of now starting into the nitty-gritty details, because we build up on this example and did exactly what Andreas just told. He wanted to create it as flexible as possible. So this is what we now will take a look into next, with the basic scenarios, which will get more complex the further we proceed in this workshop. So let us start into it with the Veterans and Administration Lung Cancer Study. So here we have a randomized trial of survival times under two treatment regimens. The treatment regimens are either standard or test, so 0 or 1. and it's for lung cancer. So the endpoint is either censoring or death. And we have this Karnofsky performance score, which we will first consider to be a linear effect, and then later we will build in the time varying effect. So you briefly saw what our task was here before. So we wanted to see if it matches our Cox pH model. And now let's take a look at how the code looks like. So on the left-hand side, we have our Cox model, and on the right-hand side, we have our pump tools code. On the left-hand side, what you can see is that basically to fit the linear model, you call the Cox pH function, include the survival data set, and just specify your model. So here the model consists is basically the survival object time and status, and you regress it, or you regress it on treatment, the prior therapy, or the Karnofsky score. And then when you will type in summary and all that stuff you already know also from linear models, you get the results of the Cox model of the log hazards. On the left-hand side in the table, we plotted the results. On the right-hand side with PAM, basically it's almost the same. It's just that you need, for pre-processing, you need this this SPD step first. So you have to create your piecewise exponential data first. This is done on the top part, the data transformation. You then can you then just after that call the function PAM in the same way or almost the same way as your Cox pH function. And instead of including the survival data directly, you can include the PD object. And after that, again, you can use the summary function or what a summary function to then check what the log hazards, like the betas of your log hazards, look like and how big they are. And basically, the thing is, so what we wanted to point out is for a linear model, it works almost the same as in the Cox pH model case, but we just have this one further step with the data transformation, which is implemented in this SPD function and can be called easily. Maybe for those of you who are not familiar with this kind of setup here, this arrow to the right, it's basically, it's just this operator in R. It's either this percent greater percent, or it's this a vertical line and greater, but just here showing it on the slides, it's just transformed to this arrow, but this is just this pipeline operator in R. And then what you can see is that these examples are fairly similar, right? And of course, in both cases, we omitted the summary statement, but in both cases, you also get confidence intervals, which makes it easier for you to then actually see if you have an effect or not. And if I remember correctly, for treatment and prior, we did not see an effect. So the confidence intervals included the 0 in this case. And for the Karnofsky score, it was significant, if I remember correctly. But so far, so good. But this is not, so this here, we now know everything works the same, but this is not what we want, where we want to head. What we want to head is really exploit this flexibility and exploit the possibility to model effects smoothly and not just linearly.
I can
yeah,
take
let's
this example just briefly because I created this example here. Yeah, so this is just to show how you can now use very flexible additive modeling to obtain nonlinear effects. Yeah, so in this case, we investigated the response times of fire brigades in London. Yeah, so how long does it take until after an emergency call they arrive at the scene of the emergency? Yeah, some variables that we investigated here were time of day, so time numeric here, and also the coordinates at which the emergency call was placed. And as you can see at the bottom, we call again the PAM function. So I skip the data transformation here because it's always the same with the SPD function. But then we call the PAM function, yeah. So and we have the baseline hazard first, and then you can see the second row S of time numeric. we fit a so-called cyclic spline, yeah, because we have the time of day, and 0 hours and 24 hours should have the same effect because it's the same time point. And this is, for example, something we could not easily do using Cox function, although it has a p-spline function for nonlinear effects, but for example, no support for cyclic splines. Yeah. And on the right-hand side, you can then see the estimated effect. You can see that during 9 times, the hazards are lower, which means it takes longer to arrive at the scene of emergency. Yeah, so the response times are longer in the night. During the day, it gets better, but we can see another dip during the rush hours where there's a lot of traffic between maybe 12 and 1600. Yeah, so and you can see you can really model these smooth and nonlinear relationships. And then the next term, this TE term of dot x and dot y, is just a tensor product spline of the coordinates x, like eastward and north-south and east-west. And you can see here on the x-axis is the east-west direction, on the north on the y-axis the north-south direction, and red colors mean positive hazards, blue colors negative hazards. And you can see that in the city center, the hazards are higher, so shorter response times to emergency, and then the outskirts, longer response times to emergencies. Yeah. So, yeah, just wanted to include this example because for the rest of the tutorial, we will focus more on the different survival settings and more simple settings. But this just to show you that you can really do flexible time to event modeling with complex effects.
Thanks, Andreas. And I think also this concludes the proportional hazard section. So let's continue with the non-proportional hazards. Let's first clarify what changes now in the setting. So so far, what we had was that our effect of the covariate x did not change as time progressed. So we did not have any interaction between time and x, but this might be feasible that this is the case. For instance, think about if in the medical framework, think about a patient being admitted to hospitals, and some tests were run, and these tests are these tests suggest certain numbers are too high or whatnot, but this can also change over time. So after 3 or 4 days in the hospital, it's questionable if these numbers, if these tests you've run are still as predictive as they are after 4 days. So in this case, we might want to think about how these covariates change over time. And basically, what you could do is you make them artificially time dependent. Artificially, why? Because you now basically just interpret it as an interaction between covariate and time. And this can be done either linearly, or when you specify the function of the time, or you can also do it smoothly when you just say, okay, now my time component is some sort of spline, which is denoted with this S of time here, and the interaction with the time spline I get by basically multiplying it with x, but linearly. So this is the first case with S time by x. We'll take a look into those, but then also this might be interesting. And here with the tensor product splines, you just have seen with the x and y coordinate in this fire brigade example. But if you think about it, the time is continuous. If you have a covariate which is continuous, you can easily do this tensor spline product also with time and covariate, and then you have a more complex structure. And we will analyze both the first the linear case, and then a case where we combine, where we interact linear covariate with a smooth time. And for that, as I already told you, we revisit this Kanowski performance score example. But now what we do differently is we model this Kanowski performance score as a time as a time varying effect, but still treatment and prior therapy won't be taken. We just change now the Kanowski performance score. And here, especially in this case, the literature suggests that we have this delay of 20 days, and the time dependence is logarithmic. So here, extensive literature has built up this theory that our Kanowski score interacts with a delayed logarithmic timescale, basically. And if we want to model it like that, I mean, first of all, as always, we need again to produce this PD data set, so piecewise exponential data with the SPD function, and then we include this logarithmic delay time effect here as another variable. And when we want to fit our model, we can again do it with PUM and then just plug it in here and have the interaction term in the end of the Kanowski score and the logarithmic time. Exactly. So this would be one possibility. This could also be done with Cox pH modeling, with this Cox pH function. So this would still be fine. But if we would not have, if we haven't had such a great extensive literature research on this time effect, we could, or me as a statistician, I did not know. Basically, I'm not a medical expert. So I could still model it bluntly with this as T end, and then interact it with the Kanowski score and make it variable, make it possible to take up this form of the logarithmic if the data suggests to. But then also with these splines, what's important is that you are also not prone to overfitting. So you try to penalize the amount of parameters you estimate. You try to penalize how wiggly the spline can be, just to not fit the data perfectly, but to have a smooth effect which approximates the data well, but is not is not an overfit. And we both fitted the two models, so the log T model and the time varying effect using the spline. And here in this case, we see that the AIC, so the archaic information criterion, is not very, so the difference is not so big. And actually, so the log time example is a little bit better because the AIC is smaller. So basically the AIC, for those of you who need just a quick reminder, it analyzes the amount of parameters which we have to estimate in our model, but on the same time, it checks how good the model fits the data. And we want to minimize it. Here it's almost the same. So we would conclude that that in this case, the model with the log time would be good enough. But I mean, when you do not have such great literature based research before, then you wouldn't know how to model the time, and then this spline can be very useful. And we also did plot both effects. Maybe let me quickly go into the details here with the make new data again, just so that everyone understands what happens here. So to plot it, basically we did our pre-processing, we did our estimation, and now it's the post-processing. We now build up our data set with this function make new data. We include in our data set all the time points. And then we basically add our function. So with add term, you can add the object which we estimated, evaluated at the input Kanowski score. And then having this inside our data, of course, we then have a second we have a second time series in our data, which we then compare our spline to. Then having both in our data, we can then use, I mean, I prefer ggplot, you might prefer something else, but then we can use our preferable visualization tool. And here we can see in red this log t plus 20, so the delay time effect, logarithmic delay time effect, and then in bluish we see the spline. In the first part, it fits quite well. In the second part, Andreas and me, we discussed which might be the better fit. Here, he suggested that over time, the Skarnowski score might not have an impact on the hazard again. So I like this interpretation quite a lot, since it also is exactly like the example with the medical data we had. When you enter the hospital, some values you get checked, but then over time they lose their predictive power. So, I mean, but overall, I think the takeaway here is that the difference is not huge. The red curve still lies in the confidence intervals. And overall, when we have a lot of data right in the beginning, the fit is almost the same.
Okay, maybe I can just briefly talk about stratification. So, as you know, for the Cox model, you can non-proportional hazards either by having time-varying effects, or you can have different baseline hazards in different categories, in which case you use stratification. And this is easy to do. Yeah, so in pumps, you just include the variable with respect to which you want to do the stratification, so the strata variable. And then for the estimation of the baseline hazard, you also just include the interaction. So in this case, we again look at the tumor data. So in the first row, you see within the pump model with ST end by complications. Yeah, so complications just is a factor variable, which means we will estimate 2 different baseline hazards for patients with and without complications. And then in the next line, again, the usual workflow. We use the data set, create new data from that data set with all the time points, and complications are unique complications. So this will create a data set where for each level of complications, you will have all the time points that you have in your data set. So it's kind of similar to expand grid in that sense. And then we just group by complications and calculate and predict the hazard and survival probability and add them to the data set using the add hazard and add surf prop function. And then again, we can use this data set to create the plots. And we can see that clearly here is non-proportional hazards with respect to complications. You can see in the hazard, patients with complications have a much higher hazard in the beginning, which then, however, levels off quickly to a normal level. And you can also see in the survival probabilities on the right-hand side that the survival drops quickly for the group with complications. But then in the end, the overall survival in the end is quite similar to the ones for the group without complications. Yeah.
Okay, and this concludes the non-proportional hazard section. Let's come to our last nitty-gritty detailed section, the event history analysis. First of all, let me give you a quick overview what we did so far. So far, what we did consider was single event data, for instance, death or accidents in the fire brigade example, and so on. But however, sometimes we are interested in competing risk scenarios where as we the ICU example, where the discharge competes against the death, or at some point when we have different stages, severities of diseases, we might also be interested in multi-state settings where we can transition to more severe stages of diseases and come back again or die. So it's somehow a mixture of recurrent events and competing risks. And in general, all these settings are called event history analysis. And first, we will start with the easier one of these, which is the competing risk setting. In our example, we have not K risk, we have 2 risks. We have this ICU patients with either status 0 for censoring again, status 1 for discharge from the ICU, or status 2 for death. And as I told you before, either we we can see the death in our data, then the patient cannot be discharged from the ICU. Or we see the discharge from the ICU, then we cannot see whether the patient dies or not. And our variable of interest is pneumonia status. It's either 0 or 1. And what we want to do is we want to see if pneumonia actually has an effect on mortality or not. And beneath you see again the data, this from the MBNA package, and you see some covariates, age and sex, and you see the pneumonia status. And of course, now what's different is your status does not only have 0 and 1, it also has more than this. It has another level 2. And the nice thing about this PED function as PED, it automatically realizes whether or not you have more causes or more stati than just 0 and 1, and then it transforms the data respectively. So yeah, to competing risk setting, and adds, if we have this combine equals true, basically what we do is, what we could do is we could separate the data set for each state transition, have one data set, and then estimate on this smaller data set the transition hazard. But what we can also do is we can put them all together and add another, basically somewhat like a long format, and add another variable called cause, which then tells us which transition just happened. So does it go into discharge or death? And then again, it's again the function PAM, which can be used. This time we need to, what we just saw in the previous example with the stratification, we need to include the cause here as an interaction of time, because we want to have the cause-specific hazard. So we have this interaction between time and cause. And then we also want to model the interaction between the different causes and the pneumonia. So we expect that pneumonia has a different impact on death than it has on discharge. So here we model it also as an interaction. And in the end, when we, here you can see the summary plot with the confidence intervals and the different estimates on how strong the effect is. And then if we put all together and consider this interaction term, we actually see, this is the bottom line, that our hazard estimate of death, if you have pneumonia, is below 1. Which would suggest that the risk of dying with pneumonia gets lower. The hazard ratio is below 1. So, but then what you also see is that our confidence intervals include the 1. So it's actually not quite clear whether this estimate which we see is the right effect. So it could also be greater than 1 in a slightly different subset. So here we still don't know whether we should trust this effect. And this data, what we saw, the confidence intervals, including the 1, doesn't show us that pneumonia might not have a clear effect on the death hazard, but we cannot conclude that this says that we do not have an effect, that it does not have an effect on mortality, because we want to know whether patients with pneumonia are more likely to transition from being in the ICU to death rather than transition from being in the ICU to discharge. And to do that, we have to add the cumulative incidence function. And again, what we do is we basically build up our data set on which we want to evaluate this this cumulative incidence function. We do that with T-end, pneumonia, and cause. We take all these unique, so all possible variations are now in our data set, and then with this add-civ, we basically include our cumulative incidence function to the new data frame and can now plot the cumulative incidence function. And here we can see that it reduces the probability to transition into discharge. So if you have pneumonia, it reduces, this is the blue line, it reduces the probability compared to no pneumonia to transition into discharge. And then for death, it increases it. So there is an effect on mortality. Also what you can see is that if you were admitted with pneumonia, you stay in the ICU longer, which you can see here for these discharge graph. And so basically here again, to summarize, we with this Additive, we had a simple possibility to model competing risk data without having to think of how to transform the data correctly, because this was done with SPV. And then since we are running a bit out of time, let me quickly come to the last example, the multi-state example. Now we are on the right-hand side. In our example, we will have we will transition between 1 and 2, 2 and 3, and 1 and 3. So the 0 state is not there. It's just you can transition from 1 to 3 in our example. And what is this? So here we check the prostaglandin levels. We have different states, 1, 2, and 3. 1 means that we have normal prostaglandin levels. Then 2 means that these levels are abnormal, and 3 means that we died or the patient died. And then between normal and abnormal, we can transition back and forth, and into the death state, we can transition either with abnormal or normal prostaglandin levels. The thing now is, because we can transition back and forth, we now only the time does not suffice. We need a start time and a stop time in each state, because it can happen that one patient goes from 1 to 2 at time 0, and then stays in 2 for a bit. But then how would we measure when the patient transitions from 2 to 3 if we do not have the start time of the patient in state 2? So this seems to be a little bit more complicated, but this is actually not the case, since we can just change, include it in our survival object here. And the only thing which has to be done is, because now that it's so flexible and we can basically transition from state 2, for instance, either in state 3 or back to 1, we need to add all possible transitions at this point in time. And this would be tedious to do. So what we do is that we use the helper function add counterfactual transitions, and this does the job for us. And then with the SPD, we then arrive, maybe you can skip that, again at the modeling. And if I want to model, it's the same. If I want to model the different baselines for different transitions, I can do that by having an interaction between the time and the actual transition into which state we're going. And what I'm interested in is the treatment effect of this prednisone against placebo. So this is also modeled as an interaction based on the transition, because I want to know whether it has an effect on transition from abnormal to normal or into death, and this can be done with this interaction. And then again, we build our new data, and to have the transition probabilities similar to having the cumulative incidence functions, we then adjust the add trans prop of our object, of our hazards, basically estimated hazards. And this function, this add trans prop, includes now our transition probabilities in our data set, which we can then plot again and display as here, for example, in a facet wrap plot, where we have in each facet the different transitions. And what can we derive from this plot, for instance? So right now, I mean, what's still work in progress are the confidence intervals, but they will be soon implemented. So we can also make a statement on significance. But what we see is that prednisone treatment slightly reduces the transition probability into the death state. For instance, here, prednisone is blue, placebo is red, so we see it in this second facet. But then the differences between the probabilities are small, so we only have a minor effect of prednisone compared to placebo. And this concludes our examples. Let us maybe quickly summarize what you have seen, because this was quite a lot. So basically, for the pre-processing and post-processing, we showed you some useful functions. For the pre-processing, it's this SPD function, which can handle all different settings from single event to multi-state. For the post-processing, very important function is this make new data on which we then can evaluate our estimated object. But in case you use PAM, and MGCV, we implemented this at survival probability, at hazard, at cumulative hazard, cumulative incidence function, and transition probabilities. So basically, they calculate all the things you want to show, the things you want to visualize for you in your newly created data set. And then there are also convenience functions for visualization, which we couldn't tackle in this 1 hour today, but I'm sure there's something on our homepage, of the PAMTools homepage. And maybe, Andreas, you want to say something about the outline and what's beyond the GAMS?
Yeah, sure. I mean, we basically finished. Just want to mention that we focused here on GAMS estimated with the MGCV package, which makes sense because it's the default and probably best package for generalized additive mixed modeling in R. But depending on what you need, once you transform the data, you can use GAM4 if you need more flexible random effects. You can use the SCAM package if you want to introduce monotonicity constraints on your smooth functions that, for example, they always go down because that's what you know from substantial knowledge. If you're more into Bayesian modeling, you could try BRMS package. Or if you have a lot of covariates and want to do variable or term selection, you could also try to boost the GAMS using MBoost, for example. So currently, most of the functionality of PAMTools is customized to MGCV GAMS, but it's not that easy to extend. So essentially, you just need to write some S3 functions that take the PED object and the model object and then return the predictions. Contributions are welcome. If you have a favorite package that you want to add to PAMS, reach out or go to the PAMTools GitHub repository and post an issue there, or ideally pull request. So we're happy to receive contributions. And just to wrap up, if you have any questions or if you have difficulties to apply PAMS to your data set and want to try out, you can reach out anytime. Yeah. And with that, I would think we will conclude. But if there are any questions, we're happy to answer questions. There was one question in the Q&A that I'm happy to elaborate a bit more on. But if there are other questions, we're also happy to receive those.
Yeah, thank you for attending.
Exactly. Yeah, so maybe if there are no immediate questions, I can briefly go back to the point on how they handle large data sets, how PAMS handle large data sets. Johannes, if you can open up again the slides with the fire brigade example.
Yeah, sure. 1 second.
Yeah, so maybe to elaborate a bit, since we do the data transformation, we get more rows in the transformed data than in the original data set, which makes the data larger and therefore computationally more expensive to fit than in the original state. for example, using Cox model. However, for normal size data sets, the differences are really not practically relevant. Yeah. However, depending on the setting, the data set can become quite large. However, there are techniques also implemented in MGCV GAM, and there are also papers on that from Simon Wood, which makes the estimation of these types of models on really giga data sets with millions of observations quite feasible. Yeah. And an example for that is here. So when you look at the code, we fit the normal PAM model, but then for the additional arguments are specified that the engine should be BAM, which stands for big additive model. And then discrete equals to true also is an implementation or an option that makes even more efficient to estimate splines. And then method FREML means fast REML, which is another optimization for speed. Yeah. So, and using these options, you can really fit the models much quicker. And we did some comparisons. The performance doesn't really degrade noticeably. So that's a great option to just make the estimation quicker. And it's not in here, but you could even include a parallel option. So it would split up the data set in different chunks, estimate the parameters on each of the separate chunks in parallel on your computer, and then re-aggregate all the estimates to obtain the final estimates. Yeah, so using all these options, it's also really applicable to larger data sets. Okay, so I don't see any other questions.
No, me neither.
Chat or in the Q&A. Okay, then I guess we can finally conclude. Yeah. So thanks again, everyone, for the attention. And yeah, as I said before, if you're interested in any of this, don't hesitate to reach out. Thanks.
Thank you. Bye-bye.